This synthesis is what allows generative AI to create content that feels authentic and coherent, because it's not simply copying, but truly understanding the essence of the data. One of the most groundbreaking architectures in generative AI is the Generative Adversarial Network, or GANs, introduced by Ian Goodfellow and his colleagues in 2014. GANs are unique because they employ a two-player game theory approach involving two neural networks, a generator and a discriminator, locked in a perpetual competition. The generator's task is to create new, realistic data, for instance, fake images, from random noise. Simultaneously, the discriminator's job is to distinguish between real data from the training set and the fake data produced by the generator. This adversarial process drives both networks to improve. The generator continuously learns to create more convincing fakes to fool the discriminator, while the discriminator gets better at detecting even subtle imperfections. This dynamic interplay pushes the generator to produce incredibly high-quality novel outputs, making GANs instrumental in tasks like realistic image synthesis and style transfer. Another foundational architecture in generative AI is the variational autoencoder, or VAE. Unlike GANs, VAEs take a different approach to generation, focusing on learning a compressed, continuous representation of the input data known as a latent space. A VAE consists of two main parts, an encoder and a decoder. The encoder takes an input, say an image, and compresses it into a probability distribution within this latent space, not just a single point, allowing for more nuanced representation of features. This latent space is a lower dimensional representation where similar data points are clustered together, capturing meaningful variations. The decoder then takes samples from this latent space and attempts to reconstruct the original input or generate new, similar data. The variational aspect ensures that this latent space is well-structured and smooth, allowing for meaningful interpolations and the generation of novel, coherent samples by sampling from this learned distribution. VAEs are particularly good for tasks like image denoising, anomaly detection, and control generation. While GANs and VAEs laid crucial groundwork, newer architectures have pushed generative capabilities even further. Transformers, initially developed for natural language processing by Google in 2017, revolutionized sequence modeling. Their self-attention mechanism allows them to weigh the importance of different parts of the input data, enabling them to generate highly coherent and contextually relevant text,